Hello learners and welcome to practice exam number 2 with a focus on chapter 12 and 13. Now similar to exam number 1, exam number 2 will be 20 questions and you will be given an hour and a half. Similar to exam number 1, we have similar goals. We know that learning is a process. We know that we want to have completed all the lecture and homework material and also have a strategy and approach for each and every question. And of course that includes practice and review. And you want to continue to repeat that as necessary so that you can help yourself lower anxiety and also be able to get through this exam and get the outcomes you're looking for. Now, of course, during the exam, you can ask questions while it will only help guide you based on your own. Okay, so number 1 says, given the following balance equation, determine the rate of reaction. So they're asking us about the rate of reaction. That's going to be the first thing that comes in my mind. And I'm like, what is the rate of reaction? So we know the rate is equal to the change in some concentration of reactant or product divided by the change in time, okay? And they said they want the rate of reactions with respect to Cl2 based on this, again, balanced chemical equation. They said if the rate of disappearance of Cl2 is 4.82 times 10 to the negative 2 molarity per second, what is the rate of disappearance of NO? That is the question. And so disappearance means that Cl2 is decreasing. And that also, in my head, means that Cl2 is probably a reactant, because usually when we're thinking of rate of reactions, our reactants are decreasing to produce the products, right? And so the first thing I'm going to do here is take my overall balanced chemical equation here, and I'm now going to write the rates in relationship to all of them. So we can literally take our coefficients that are in front of each of our species here, and we can use it to our advantage, again, to create the rate. So for all of our rates for our reactants, they will be negative, and for our products, they will be positive. So here we'll have negative 1 over 2, okay, the change in NO divided by the change in T. This is going to be equal to negative 1 change in Cl2 divided by the change in T. And this is going to be equal to positive 1 over 2 change in NOCl divided by the change in T. All right, folks. Now, what else have they already told us? They've told us that this here, the rate of disappearance for Cl2 is going to be equal to 4.84 times 10 to the negative 2 molarity per second. And they want us to find the disappearance of NO. So that is our goal. All right, folks. And so what we can do is use the fact that these two reactants are equal to one another, and use what's given to help solve for the variable in question. So we know that this entire thing is equal to negative 4.84 times 10 to the negative 2 molarity per second, and we're saying this is equal to negative 1/2. And of course, we can just write x here because that is the variable we're looking for, but I'm just going to go ahead and write the rate. That's our x value. So to solve for this rate here, we're going to multiply this by negative 2 over 1. So now I'm going to multiply this side by negative 2 over 1, okay? So that means my change in NO divided by my change in T is equal to negative 2 times negative 4.84 times 10 to the negative 2 molarity per second. So that means my answer would be, I'm going to put in my calculator, 9.68 times 10 to the negative 2 units molarity per second, and that would be the answer, which for me is going to be letter D. All right, now for number 2, it says determine the rate law and the value of K, which is a rate constant, for the following reaction using the data provided. So first we have to say, what is a rate law? And we can use the reaction that's given to help us write a generic rate law to help us figure out exactly what we want to be looking for. So we can say our rate is equal to the rate constant times our reactant concentrations raised to a particular order, which we do not know yet, right? So we have our NO raised to a power of X, for example. Sorry about that. And then we have our O2 raised to a power of Y, for example. Now, they want us to find the rate law itself, the overall rate law. They want us to find the K value. But in order to find the K value, we need to know the rate, we need to know the actual order in relationship to each of these reactants, and that's all going to be based on data. So some students might say, oh, there's a 2 here, there's a 1 here, and they might automatically just say that that is the order. But it's very different from number one. Number one is a crude version of how we learn about rate. Number two is an elevated version of how we learned about rate by including concentrations of reactants and how they influence rate, and also including a brand new variable K, which is the rate constant. And then we go further and say, well, if we want to see how concentration and temperature affects rate, for example, we're going to take our concentrations and we're going to have them be related to an order. And that order is going to be zero order, first order, or second order. And depending on whatever order each of these reactants are related to, that's going to tell us if our rate's going to be triple, double, halved, whatever, okay? And so this is kind of taking that rate information from number one and elevating. Now, the only way to get these variables is by completing what we call the method of initial rates. That is, the method of initial rates, just like any other reaction rate, means that you have to use data that's given, and you're basically going to search through the data and find areas where the concentration of NO is the same. And so if the concentration of NO is the same, we can ignore it so we can focus on the concentration of O2 and therefore find the order. We do the same thing and scour through the data to find where the concentration of O2, for example, is going to be constant so that we can focus on the change in the concentration of NO and find the order. We also are going to be given rate data as these concentrations change as well. What kind of rate data? The initial rate data. Now, we talked about different, and of course, if you go in the lecture, we had our guest lecturer, we talked about different average instantaneous rate, average rate, instantaneous rate, and also initial rate. Now, the initial rate is an instantaneous rate, but at zero, time zero. So at time zero, we don't focus on products, we focus on reactants, right? That's the reason why we see our rate only connected to reactants. And so when we're thinking of method of initial rates, that's the reason why you'll see any of your rate data say initial. All right, folks, now let's go ahead and get to this. The first thing we want to do is just focus on where our data is. That's what my brain goes to. So I'm like, let me find the data. We want to find where NO is constant so we can focus on O2. And then we want to find out where O2 is constant so we can focus on NO. So I'm looking through my data. I see NO concentrations here. We only need two. That's when they're going to be the same. And so that means I would have rate 1 and 2 here. And then for O2 concentration, it looks like, let me write rate 1 and 2 we can use here. And then for O2 concentration, it looks like we have this here, rate 1 and 3 are going to be the ones that are the same. So we're going to use this to our advantage to solve for either of them. Doesn't matter if you want to figure out the rate, or sorry, the order of NO or the order of O2 first. I'm going to start with O2. I don't know why. So that's just how my brain goes. So if I want to figure out the order of O2, which is going to be that Y value there, then I have to figure out when my NO is going to be the same. And so that's going to be rate 1 divided by rate 3. Okay, that's when they're going to same. And that means that I'm going to take my O2 values. Okay, so I have my O2 value raised to the power of Y, and then I have my O2 value raised to the power of Y, because that's what we're trying to solve, right? Now, what do? We plug in the numbers that are in our data table and related to everything that we see here. So my rate, instead of writing rate 1, I'm going to write the rate here, 8.55 e to the negative 3 milliliters per second, divided by rate 2. Remember, we're focused on the rate where NO is constant, which is 1.71, okay, e to the negative 2 molarity per second. This entire thing is equal to concentration of O2 for the first rate, 0.0055 molar. And then, of course, the concentration of O2 at rate 2 here, which is going to be 0.0110 molar. Boom. And this entire thing is raised to Y. Why can I do this? So instead of having them divide by each other because they're both going to be raised to Y, I just simplified that. Okay? Now, what do? I do the math. So when you do the math, you're going to see that you get 0.5 here. And this is going to equal 0.5 raised to the power of Y. Now, as you can see from here, it's easy to basically just simplify and say, well, what number can I raise this number to in order to solve for 0.5? And the only number it's going to give us is 1. So I can automatically say here, Y equals 1. All right, I don't have to do any extra math or anything like that. I can just use logic to get through. Because if this is 5, 0.5 raised to y, if I say this is 1 here, I'm still going to get 0.5, so therefore my y is equal to 1. Let's go ahead and get our next variable. That means this 1 can be here, and that means our order for O2 is going to be reaction order of 1. Let's go ahead and do our x. Now, in order to find our NO, we got to figure out when our O2 concentrations are the same. So that's going to be rate 1 divided by rate 3. And that's going to equal to our NO concentration x divided by our NO concentration x at whatever that data is giving us, right? And so what does that mean? Rate 1 is still going to be 8.55 e to the negative 3 molarities per second. And this is rate 3 is still going to be 3.42 times 10 to the negative 2. Okay, 3.42 times 10 to the negative 2 molarity per second. This is going to equal to concentration of NO at that time at rate 1 is going to be 0.030 molar. Concentration of NO at rate 3 is going to be 0.060 molar. This is all raised to the power of x. Huh? Great. So we're going to do the same thing. We're going to do our math here. And when we divide these two numbers, we get 0.25, right? And this is actually equal to 0.5x. So as you can see, some folks will just say, well, automatically x is equal to 2. But some of us, guess what? We won't be able to go through logic when we have smaller numbers. So another way to do this, if you do not want to use logic, was going to be taking the log of each side. When you take the log of each side, you can actually bring x down. Okay, so this will now be log of 0.25 is equal to x log of 0.5. So now I can divide by log of 0.5, divide by log of 0.5, so my x is equal to 2. So it just depends on how you want to get through. What is this telling me? This tells me that if I was to go back to my rate up here, instead of writing x here, instead of writing y, I can now write NO has an order of 2, and O2 has an order of 1. And a lot of times when you have an order of 1, they don't write it. So just by that information, they want a full rate law with all the numbers and all the bells and whistles, right? So we've already got our orders in relationship to our concentrations. Now we just need our K value. Before we do that, we can go through our answer choices and start getting rid of stuff that we know doesn't have the correct orders. So for example, A doesn't have the correct orders, B doesn't have the correct orders, C doesn't have the correct orders, and neither does E. Automatically, right? Letter D has to be correct without even finishing the question because you've already were able to do process of elimination. But of course, we got to go further and finish this up, right? You definitely want to stop there. Some folks are like, finish it up, bro. So that's what we're going to do. Now, we know our answer is D at this point, but let's go ahead and get the rest of the numbers. How do we get that K value? Okay, so to get that K value, we're going to take our rate, we already know, is equal to K. We have NO raised to the order of 2. We have O2 raised to the order of 1. If we divide by NO raised to the order of 2, O2 raised to the order of 1, then we can isolate K by itself. And we just divide them over here, divide over here. So now our K value is equal to rate, NO raised to the power of 2, and O2. And a lot of folks say, well, how am I going to solve for my K value? Which rate do I choose? Which NO do I choose? Which O2 do I choose? You focus on the trial. So this is all trial 1 data, trial 2, trial 3. You can choose any of those trials and you want to use all the numbers from that trial. A lot of times you just go with trial 1, and that's what I normally do because I'm like, it's just easier for my brain. I go with the first one. Also, I was born on the first. So for some reason, I always go with the first as like the number 1. All right, so 8.55 e to the negative 3 molarities per second. We want to focus on units because that's going to matter too. We got to make sure we get every single thing here if this is our correct answer. And then for NO, we have 0.30 molar. This is going to be squared. And then we have 0.0055 molar for O2. And so again, we're going to have 8.55 e to the negative 3 molarity per second. Now, I like to do my math on the side here. So this 0.03 here is now 0.0009 molarity squared. So if I have molarity squared times molarity, that means the bottom here should be molarity cubed, right? And when I multiply these two numbers, I get 4.95 times e to the negative 6. So what I did is I took my 0.0009 molarity squared and multiplied by the 0.005. That's how I got 4.595, sorry, times 10 to the negative 6 molarity cubed. Now, of course, I can get rid of my molarities here, so this is just going to be squared here. I have 1 over seconds here, and I have molarity squared. So my units, I know, is going to be 1 over molarity squared and 1 over s squared, right? So, or s to the 1, sorry. So that's how I'm able to verify my units there. Now, of course, I still need more room. Let's go ahead and get my k value, get a different color here. My k value, and let's see significant figures. I have 2. 2 looks like my lowest number is 2. So I'm going to go with 2 significant figures. Once I actually do my math, I get 1.7. Again, the units are 1 over seconds over molarity squared. Okay, so this is really molarity squared over 1. So we're going to go 1 over molarity squared times 1 over molarity squared. And that's how we get our u. So this is really 1. You can write 1 over s molarity squared, or you can write m to the minus 2 seconds to the minus 1, which is what we see here. That's how we got our answer, folks. So me off rip, I started doing methods of initial rates, and I focused on the orders. Then I do process of elimination. When you're on the exams, when you're even on the finals, whatever, any exam in the future, you want to make sure if you're given multiple choice, always think of process of elimination. Okay? So you end up doing half the work sometimes instead of having to go through the whole thing. All right, folks, let's move on. All right, welcome to question number 3. Now, off the bat, guess what, folks? Yes, this is my issue. The correct answer for this is definitely not letter E. That is not correct. Okay, no. So letter E is not the correct answer. Sorry, folks. The correct answer is actually letter B, and we're going to see why. Now, again, I actually wrote this when I went back to the answer. Good thing I redo and I go through all my exams on my own. This is how I figure out if I have mistakes. And I did find this mistake. So I'm like, and I went through everything. I'm like, no, it's a mistake. And so I'm able to tell you that letter E is not correct. Is not the correct answer. Correct answer equals B. I will have a little note above this video just to let everyone know that as well, just in case you don't need help with this portion. Okay? All right, folks, now let's actually get started inside the actual question. So number 3 says the first order decomposition of N2O5 at 328 Kelvin has a rate constant of 1.70 times 10 to the negative 3 seconds to the minus 1. So from the first sentence, it says first order decomposition. Okay, so we know we're dealing with the first order reaction, and we verify that with our rate constant being units of s to the minus 1, which are the units for first order, but it doesn't really tell us anything else to do with it. So we have to continue to help us get more information. It says if the initial concentration of N2O5 is 2.88 molar, what is the concentration of N2O5 after 25.2 minutes? All right, now we got some details. So we know it's first order. Now I can write that down. What else do we know? We know we have a rate constant of 1.70 times 10 to the negative 3 units of second to the minus 1. We also know that the initial concentration of N2O5 at time 0 is equal to 2.88 molar. They want us to figure out the N2O5 concentration after 25.2 minutes. So that means they give us a time of 25.2 minutes. Now, when we're thinking of first order, when we're thinking of rates, we saw in the previous questions, we looked at rate, right? From question number 1, we looked at rate for question number 2 as well. And the only time that we see time as a variable is in this question. So that means we have to look at another expression of rate. And one of the other expressions of rate is going to be based on the individual orders. And those are going to be our integrated rate laws, which allows us to have those linear relationships. So integrated rate law is going to allow us to have linear relationships and use the variable time. So anytime you're thinking of time, whether it's half-life or time in general, you need to be thinking of integrated rate laws, okay? So the integrated rate law for first order is the natural log of whatever your final time is. This one is 25.2 minutes, is equal to minus KT, so it's a negative slope for a graph, okay, plus natural log of whatever your initial concentration is. For us, they already kind of gave us these numbers here. We already know this is 1.7 times 10 to the negative 3 seconds to the minus 1. We know this is 25.2 minutes. We know this is 2.88 molar. They want us to solve for this particular variable. So we got to get rid of natural log. And so these are all details that we're getting just from understanding this information. This is how you want to be, just seeing this and being able to say, boom, boom, this is what I'm getting at. Now, let's talk about, Professor, are you going to be giving us second order and zero order and all this stuff? No, I'm going to give you straight up, okay? Reason why is because a lot of the questions that you get in the future as well, a lot of the questions that we see are first order questions, okay? And so if you have zero order, second order, yes, you can kind of use the same equations and use the same kind of solving for variables to help you get through. But as far as the exam goes, we're going to be focused mainly on first order. But no matter what, you're given these actual reactions, right? You're given, no, not reactions, equations. You're given these equations on that formula sheet. So I would make sure that I know these equations and know how to utilize them. That's two things. So you want to be able to recognize them, you know, just by looking and just by reading the questions. You want to be able to derive them just by seeing them as well. And you want to be able to manipulate those variables. So keep that in mind. Sometimes the trick is you're like, oh, well, they already gave me that, so I don't have to think about it. But if you're given something, that means you have to know how to do all of it, every single potential variation, because you were given it. So that should be, quote unquote, something that's easier for you. Okay? And again, I'm using air quotes, so you can't see me, because that can also be like a false statement for plenty of people, depending on how you learn it. Anywho, let's get to it. Now, when I'm going through my equation, I got the right one, I'm in first order, I'm looking at my K and T, I see they have to be multiplied. I have seconds to the minus 1 here, and I have minutes. There's no way I can multiply seconds and minutes together, because they cannot cancel, right? So I need to either convert my minutes to seconds or convert my seconds to minutes. A lot of times it's easier, because you don't have scientific notation, to focus on time. So what I'll do is I'll say for every 1 minute, I have 60 seconds. And so my time is actually going to be 1,512 seconds. Okay? So instead of 25.2 minutes here, I'll put 1512. That way I can get rid of that unit and we're all good. All right. Now all we need to do is start to either map things out or solve it how we see it here. And so let's just go ahead and do that, because I just got the easier way to do it. Boom. And so I'm going to have my natural log of AT is equal to minus 1.7 e to the negative 3 seconds to the minus 1 times 1512 seconds plus natural log of 2.88 molar. All right. You go ahead and you do the math for all of these, right? So I'm going to multiply these first. So I'm going to have natural log of AT is equal to negative 2.5704. There's no units because our seconds canceled. This is now going to be added to the natural log of 2.88 molar, which I put in my calculator straight up. That's 1.057790294 units of molarity, because we do have units here. So what are we going to do? We're going to add these together. Natural log of AT is equal to now negative 1.512609706 molar. As you can see, yes, I'm writing these long numbers. We're on the exam. I don't want to have no smoke or drama with any rounding errors. So this is what I do to get rid of any drama with rounding errors, is just simply write my full numbers. Now that I have a full number here and I just have natural log, to get rid of natural log, I'm going to take the natural log of both sides. So if I take the natural log of this side, I get rid of natural log and I just have my AT. And to take natural log of this side, which has nothing, it's going to be the antilog. So I have my E raised to negative 1.512609706 molar. Boom. Let's go ahead and get a different color here to get our answer. And so when I put this in my calculator, I do have to hit second. And then once I hit my second, I'm going to hit second. And then where you have the natural log button, right above it has E raised to a power of X. So I'm going to hit second, natural log. And then you'll see that E button raised to a power of X. I hit that, and I automatically get 0.220 molar. Now, why did I just automatically put 3 significant figures? I'm going off of what's given. 3, 3, 3, and 3. So therefore, my answer will be 3. And so from my calculator, I did get a longer number here. Because I'm at the end, I automatically just put my answer. So that's how I get B. Definitely not E, okay? Apologize for that, but that's just only one mistake. Trust me, none of the other answers changed. I went through the exam myself, so it shouldn't be any problem. All right, let's move on to question number 4. All right, so it says a particular first order reaction has a rate constant of 1.35 times 10 to the 2 seconds to the minus 1 at 25 degrees Celsius. So we have a rate and we have a temperature. Okay. The only thing that's going to help us relate temperature now, specifically to rate, if that's all we have and that's all we start thinking about, that's just the first thing I want to start thinking about. Okay, well, what relates temperature to rate? That's the first thing they're giving me. Might not have too much. Let's continue on to read. What is the magnitude, meaning what is the value of K at 75 degrees Celsius? So now they're giving me another temperature. And then it says if EA, which is activation energy, is equal to 75.5 kilojoules per mole. So I'm like, wait a minute. They gave me a first order. They gave me a rate constant and temperature. Now they're giving me a second temperature and activation energy. Guess what, folks? We're dealing with the Arrhenius equation. The Arrhenius equation is the only equation that allowed us to relate rate constant to temperature and activation energy. But there's multiple ways to express the Arrhenius equation. The only way to express the Arrhenius equation that allows us to utilize multiple temperatures is going to be the 2-point Arrhenius equation, which reads natural log of K2 with K1 is equal to the activation energy divided by the gas constant times 1 over temperature 1 minus 1 over temperature 2. And so for us, we can start plugging things in. They gave us K1 at 1.35 e to the 2 seconds to the minus 1. R is a gas constant. It is given to you. Where is it given? Right on that formula sheet. Where is this given? This equation is actually given on the formula sheet as well. So again, folks, you better be using that formula sheet. No note card. You need to be looking at everything that's potentially given to you and use it to your advantage. So this is 8.314 joules per mole Kelvin. EA was given to us at 75.5 kilojoules per mole. Temperature 1 is 25.0 degrees Celsius. Temperature 2 is going to be 75.0 degrees Celsius. Next thing we want to do is consolidate. What does that mean? Make sure all of our units are correct. Make sure we can do the math. We're using this powerful equation, and so now we want to make sure we can use the math properly. That means that we have to be able to cancel things out when they can and only be left with our K2 value here. So EA is going to be divided by our R value. As you can see, we have joules per mole here and kilojoules per mole here. So we need to make sure they are going to be the same. You can either convert this to kilojoules or you convert this to joule. A lot of times I just convert this to joule. So I'm going to take my EA value, which is equal to 75.5 kilojoules per mole, and I'm going to multiply it by 1,000 joules. And that's going to give me my 7.55 times 10 to the 4th kilojoules per mole now. Oh, sorry, not kilojoules, I said that, joules per mole. All right, now that I have joules per mole here, I can now divide these numbers properly. So that's one number change. This is good because whatever we're talking about a first order reaction, so that means K2 has to also be first order and have the same units. So we know that our units are going to be S to the minus 1 for our value here. We know it's going to be S to the minus 1 is first order. We got our numbers here. Now we got to look at temperature. We also have Kelvin in our gas constant. And so we got to be able to get rid of Kelvin. A lot of folks, well, let's just convert this to degrees Celsius. Or we can just easily convert this to Kelvin. It's going to be easier to convert to Kelvin. It's always best not to touch constants. That's the way I see it. I make everything else change to the constant. That way, I only have to memorize one thing, right? If I only memorize this and I only focus on the units that are here, then I can just change everything else. But in my head, if I start saying, oh, well, I have to do this, it just kind of confuses. So I make sure all my units match this particular unit here for all this math. So that means I got to add 273.15 Kelvin. I don't always put the 15. I'm going to keep it straight up with you. I just put 273. So for this here, it's just going to be 348 Kelvin for me. And then this here is just going to be 298 Kelvin. Yes, the 0.5 can cause rounding errors, especially after I was just talking about, I'm not going to have no issues with rounding. But this is basically negligible. That's what I've learned after all the calculations. So I don't put the 0.15. You can if you like. That's on you. Now that I have all my numbers, you already know the drill. I'm going to do different blue. I'm going to start plugging everything in. So I have natural log of K2, which is going to be my variable, 1.35 e to the 2 seconds to the minus 1. That doesn't look like seconds. Sorry. Okay, seconds to the minus 1. this is going to equal to 7.55 e to the fourth joules per mole divided by 8.314 joules per mole Kelvin times 1 over 298 Kelvin minus 1 over 348 Kelvin. You already know the drill. What do? I start breaking up my pieces. Everything has to be pieces. Okay, take your time with this. Figure it out, okay? And also, as you can see, we're barely on question number 4, and it's already like 40 minutes in, so I'm trying to. Let's just do the math. When I do this math here for this, what do I get? Just make sure I rewrite everything here. Sometimes that makes it easier. So when I do this math, that's the first thing I'm going to do. I get 9081.068078, and this is going to be Kelvin to the minus 1. Okay? Now, when I do this here, and I do this here, so I do this separately. So, and when I go ahead and get my 1 divided by 298 Kelvin, I get, and it's a long number, 3.355704698 e to the negative 3, and of course the units are Kelvin. Over here for this one, when I go 1 divided by 348, I get 2.873563218 e to the negative 3, of course units are Kelvin. When I subtract these two numbers together, I get 4.82142 e to the negative 4 Kelvin. And of course, now that I have that, my kelvins are going to cancel. And so what do? We just keep on continuing on with the math, right? I'm going to keep on here and have my natural log of K2 divided by 1.35 e to the 2 seconds to the minus 1. When I multiply these ginormous numbers together here, well, small and a large number, I get 4.37836242. No units. And then what do? I cross multiply, but I can't just automatically cross multiply first. I can't cross multiply this 1.35 e to the 2 with this 4.37 just yet because there's a natural log here. So what do I have to do? I have to take the natural log of both sides. When I take the natural log of both sides, I'm going to be left with K2 now over 1.35 e to the 2 seconds to the minus 1 is now equal e raised to a power of 4.378362342. All right, so this is where we are. Oh, man. Okay, so here we are. Oh, let me get a different color. And I'm going to move up here because you already know how it goes. Okay, so now I'm going to have my K2 divided by 1.35 e to the 2 seconds to the minus 1. This is equal to, I'm going to go ahead and do this math here. In my calculator, e raised to the power of that is going to basically, instead of doing that, what I'm going to do is cross multiply here. I'm going to keep this in my calculator. I'm going to make sure I have it in my calculator properly. And then once in my calculator, I'm going to just go ahead and keep it and cross multiply. Now I can cross multiply because I don't have a natural log here. So e raised to the power of 4.378, okay? And then 362342. This is where I get my 79.7073931. Now I'm going to cross multiply these numbers to simply get my K2 value. When I cross multiply these numbers, that's when I have to start thinking of, if I'm down to my final answer, what are my significant figures? So I have 3 here, 3, 3, and 3. Everything is 3, so that means my answer should be 3. When I cross multiply these two numbers, 1.35 times 10 to the 2, multiplied by 79.707, okay, I get 1.08 times 10 to the 4th. And of course, my units are seconds to minus 1. That is my answer. Your paper is probably going to look better than this, but even if it does look like this, all you want to do is go ahead and make sure you circle your answer, or as you can see, I'm boxing it. Box, circle, whatever, as long as you identify where your answer is, okay? So we kind of went here, then we went here, and then we went up here. All right, let's move on to question number 5. All right, we're talking about rate. We still are in chapter 12. And so the first 10 questions are chapter 12. The next 10 questions are chapter 13. So when we're talking about rate, we also can talk about one thing we can get with the rate and overall rate law and things like that is the mechanisms for the rate itself. So we have to figure out, okay, what are the actual steps in the rate itself? We can start getting details about it. But what's going to help us determine the overall rate for a reaction is going to be whatever is the slowest step. So whatever the slowest step is going to be the one that is taking the longest to help you get to whatever product you're looking for, right? So we have to say that our reaction rate is going to be dependent on that slow step. And so what we do is when you're given proposed mechanisms, you're going to predict the rate law for an overall reaction based on a hypothesis of a mechanism for this potential reaction. So here we have an overall reaction here. In order to get this, here's the mechanism that we're proposing. We're proposing that it's going to start with A2 in equilibrium to form 2A, and that's going to happen very, very fast. But in order for when A and B are mixed together to form AB, that's going to be extremely slow. So our rate of reaction is going to be based on whatever is going to be the slow. Okay. All right, folks. There we go. Our rate is going to be based on whatever is the slowest reaction. Okay. So what we do is we have to basically go ahead and propose what the rate's going to actually be based on that slow reaction. So the first thing we have to do is go ahead and make sure that we're writing the rate laws for every rate that we see in this mechanism. And so the reason why I'm saying every rate is because when you have something in equilibrium, you have the ability to go forward and reverse. So this equilibrium actually has two rates that are equal to one another. And then we have the rate here that are only going to be based on these reactions. So for the first one, we have A2 in equilibrium to 2A. The forward reaction is A2 going to 2A. The reverse reaction is 2A going to A2. And so we actually can have a rate here is equal to K, A2 based on this reactant. And you can also write K forward if you like. And then rate is equal to K reverse here, which is going to be A squared. Next, we're going to have our rate of our slow. Okay, so that is going to be A plus B. It's going to give you straight up AB. And so our rate is equal to K2. I just put 2. You can put slow here, whatever you like. And that's going to be AB. Also, because they give me an overall reaction, I'm going to go ahead and write the rate for this one. If they don't give you an overall reaction, you go off what you have. But sometimes if they give you one, you also can write the rate here. So the rate overall is going to be A2 and B squared. That is telling you the actual reactions that are going to be used overall to form these products. And so when I look at the rates here and I look at the slow rate, which is what our reaction is based off of, I have K2, A, and B. The B I can justify. That's a part of my overall reaction. But I can't justify A by itself. This is actually A2. So I have just identified an intermediate. An intermediate is going to be something that's formed in reaction and then used up, okay? And so when you have something like intermediate, you have to tell yourself, what am I going to do? A lot of times it's formed as a product, and then the next step of the actual rate is going to be used as a reactant. So that's how you kind of get rid of the intermediate in theory. But for us, because we're not actually utilizing any real variables or any real chemicals, in order for us to get rid of our intermediates here to predict this overall rate law, all we use is substitution of variables. So how can we isolate and get this concentration of a variable substituted? Well, I have to look at what was also given to me. What other rates were given to me? I see the rate reverse here has this variable. So if I solve for the variable of A and the rate of reverse, I can substitute that into my intermediate for my overall rate, and then I can find the rate of the overall reaction, which is what they're looking for. So let's go ahead and do that. I write all my rates down first. Second, I get to substitute it. So that means my K forward, which is going to be A2, is now equal to my K reverse because we are in equilibrium, and this is going to be A squared. So to isolate the concentration of A by itself, I'm going to divide by K reverse. Okay, now I have A, and this is squared, and this is equal to KF over KR, and this is A2. Now, as you can see, I'm trying to get A by itself isolated, so I have to take the square root of both sides. When I take the square root of both sides, that's going to leave my A, which is what I'm looking for, is now equal to the square root of KF over KR, and then also A2. Now let's talk. When it comes to square roots and mechanisms, we never write the square root of something in an actual rate law. So we actually have to write the exponent form of the square root. And so the exponent form of the square root is what we're going to write here. So that means our concentration of A is equal to KF over KR raised to the power of 1/2. So square root is actually, if you raise something to a power of 1/2, it's the same thing as equal to square root. If you have a cube root, you raise it to a power of 1 over 3. If you have a fourth root, you raise it to a power of 1 over 4, etc., etc. Okay? This also means that my A2 is also going to be raised to a power of 1/2. There you go. Now, the next step, did 1, we did 2, is to now substitute our A value that we just solved for into our slow step so that we can get the rate for this reaction and predict the rate level. Let's go ahead and do that. Our rate is equal to K2. Instead of writing A now, I'm now going to write Kf, Kr to the 1/2, A2 to the 1/2, and of course I still have my B left over. So remember, my rate K2 is equal to A and B. I kept my B. This A value is now this here. And of course, I kept my K2. Next thing you need to do is simplify this. And what I mean by simplify is you want to consolidate any variables that are the same. So since these are all constants here, no matter if they're raised to a power of 1/2 or whatever, you can make them one single constant because constant times constant is going to give you a constant. So that means my rate is now going to equal to K. Sometimes you'll see it put K prime. A lot of times you can just write K. K prime is signifying that all of these were actually combined, okay? And then I still have my A2 raised to the power of 1/2, and I still have my B. Now, because this is the slow step, that is going to determine the rate of the overall reaction. So now that I have my rate from the slow step for the overall reaction, and I've substituted the intermediate, I am going to see that this is my overall answer for this question. And again, I've boxed it, circled it, what have you. And that's how you approach number 5. All right, number 6, one of our graphing problems. So it says for A to products, from one reaction to products, time and concentration data were collected and plotted as shown. So we have our concentration of A molarity, and then we have our time from 0 to 90 seconds. This was plotted here. And it says determine the reaction order, the rate constant, and the units of the rate constant. Circle your answer. And everything's kind of specified here. So what happens when you have this? Again, we're talking about first order, second order, or 0 order. And we're talking about reaction rate. And again, if we're talking about reaction rate in any time, and in relationship to any form of time, that's what we're talking about, then again, we're talking about integrated rate laws. What do integrated rate laws do? They help us get a linear relationship. So if I have a bunch of data, the first thing I'm going to do is, again, graph this data as we see. And when you have concentration of A versus T, this is going to be 0 order. Okay? 0th order. Now, again, they're not showing you the other basically columns you can add to this to get the other graphs, but you could get the natural log of concentration of A and then 1 over the concentration of A in order to get the orders for the other graphs. So if I take natural log of concentration of A versus T, then I have first order. If I take natural 1 over concentration of A divided by T, then I have second order. And the goal is, when you have these type of questions, you're making sure that whatever form of data, once it's plotted, gives you a line, something that's linear, then you know that is going to be the order of the reaction. So for us, automatically, the only one that gives us a linear line is going to be, or a straight line here, is going to be the first order from this graph. So the reaction order here is first. The units are always going to be seconds to the -1. I can just write that automatically. I already have 2 out of the 3 answers. Now all I have to do is solve for K. This is where people get caught up. So they start thinking half-life, all this kind of stuff. No, if I'm thinking of first order, and I'm thinking of time, and I'm not dealing with half-life or anything like that, the only equation I can use is the integrated rate law. Okay? You can see integrated rate law has time, and it has the natural log of the concentration of A, which is exactly like the graph. What do I do now? Well, I solve for K like they want. And so in order to solve for K, I'm going to subtract natural log of AO from either side. So now I have natural log of AT minus natural log of AO is equal to minus KT. I'm going to divide by minus T. So now I have my K value. All I got to do is plug everything in, and I already have it. So natural log of AT minus natural log of AO is subtracted by minus T. Let's go ahead and start plugging things in. Where am I going to get these numbers? From the data table. That's what's great about it. So now you can choose any points you want. You're going to start initially with 0, and you can choose any time here that you like. I'm going with the second one. Why not? So if I'm going from 0 to 30 seconds, my time is going to be 30 seconds. My initial concentration, 0.500 molar. My final concentration, 0.319 molar. All I got to do is plug it in now. I have natural log of 0.319 molar minus natural log of 0.500 molar divided by minus 30.0 seconds. And so we just continue on. And I'm just plugging things in. At first, I do everything at the top. I get, let me go ahead and write this a little bit higher so I can have more space. I already know I'm running into like, real young out of space. Okay. Put this in. So what do I get? Negative 1.14, okay, 2564176 minus negative 6.93 1471806 e to the negative 1 divided by negative 30.0 seconds. So yes, I took the natural log of that and I got that, okay? So I have this whole number here. I'm going to continue on. My K is equal to negative 4.49416995 for e to the negative 1 divided by negative 30.0 seconds. We know it's first order, so we already know the units are going to be 1 over this, which makes sense. So now that I have my answer, change that color, I can see my K is equal to, and of course, how many significant figures do I actually, or yeah, how many sig figs do I have? I have 2 here from the 0. But a lot of times we don't really take it from 0, so I'm willing to accept 2 or 3 for this answer. Okay? But that's a lot of reason why we keep the data 1 decimal place for this time here. I will consider this as 2 significant figures. So a lot of times you will see it as 0.015 seconds to the minus 1 as your answer. But don't forget, you also can have 3 significant figures, which is going to be 0.0150 seconds to minus 1. So either of these answers will be correct. And so then I will just write that over here as well, because remember we have 3 answers for this. Well, 0.015 seconds to the minus 1. I would just like circle all these answers here as a group. Folks, that's how I got through number 6. Again, this is more like using graphs to help you figure out things for rate laws, integrated rate laws specifically. Let's move on to number 7. All right, another graph. So for the reaction, 2H2O is going to decompose to 2H2O. 2H2O2 is going to decompose to 2H2O plus O2. Which plot confirms the rate is first order with respect to H2O? So we're looking for the rate to be first order. I'll keep going. That's what we're looking for, the rate to be first order. And so first order rate, again, we're talking about time. We're looking at natural log of AT is equal to minus KT plus natural log of A at time 0. And of course, if we were to graph this, that means we're looking at the natural log of H2O2 versus time. And because they're telling us that that's going to represent first order, we should get a straight line with a negative slope. Now all we need to do is find the graph that looks like this, and that's it. So here we have the concentration of H2O2 versus time. This is 0th order, so we can't use that. This is second order because we have 1 over that. This is not going to be used for us. And then, of course, this will be the only one left, which is letter D. And as you can see, we have natural log versus time, which is going to be first order. That is what a first order graph looks like. So a little bit easier, and again, it does connect with the previous question, so that does help you out there. Let's move on to question number 8. All right, so number 8 says the rate law for the reaction A plus B goes to C plus D is first order in A and second order in B. So I'm like, okay, let me go ahead and write the rate for that. I can say I have rate here for this reaction is equal to K. A is going to be first order and B is second order. All right, great. And it says if A is half and B is doubled, the rate of reaction will ... So they're asking what's going to happen when the concentration of A is half. So instead of writing A here, I'll say that my rate is equal to K, and this concentration is half, and it's raised to a power of 1, and B is doubled. The double is going to be 2. And so instead of writing B here, I write 2, and that's going to be squared. What happens to the rate when this happens? And so now that we have numbers applying to it, now we can just go ahead and do the math. You can say our rate is equal to K, okay? This is going to be 1/2 times 4. 1/2 times 4 is 2. So when A is half and B is doubled, based on the reaction orders that were given, this rate should be 2 times faster. You see, I didn't focus on the constant because they're not asking about the constant, right? And it's a constant, it shouldn't change. So when you're looking at your answer choice, you're saying it should be 2 times faster. Remains the same? No, that wouldn't be working. Would be increased by a factor of 2? Yes, we know that to be true. Would be increased by a factor of 4? No, that's not true. Increased by a factor of 8? No, that's not true. Well, the only answer here to choose would be letter B. All right, folks? When you have these type of questions, just go ahead and substitute the number that they give you, whether you half, double, quadruple, substitute it for the variables of the concentration. The orders are never going to change. So whatever variables they give you, all you got to do is do the math to help you figure out how fast it's going. Okay? Let's go to number 9. Okay, so for number 9, it says the following mechanism has been proposed for the formation of ethyl benzene. So it's telling us we have a mechanism. That means we're going to have a series of steps of reactions. And what else does it mean when you have a mechanism? We're probably going to see intermediate because we already saw a reaction mechanism before where we had to get rid of an intermediate in order to write the proper overall rate law. So when I'm thinking of mechanisms, yes, we know we're going to have intermediates. And so what we have to be able to do is identify intermediates. And the way I think of it is that usually intermediates are formed as a product and then used as a reactant. What I get from there. Okay? So I'm looking at this proposal. I'm like, let me just go ahead and find if I can see anything that potentially can be intermediates based on the definition I just wrote. Okay? And I'm not even going to read the rest of the question. I'm just going through. Okay, so it has to be formed of a product. I see products here. CH3, CH2 plus, and then AlBr4 minus. Now, are any of these reactants going to be, or any of these products going to be used as a reactant? Let's see. Okay, where I do see that CH3, CH2 plus was a product and it was used as a reactant, and that's it. So yes, if I see CH3, CH2 plus, that's going to be intermediate for me. Let's see what else. We have new reactants here for this reaction, CH32 plus and C6H6. Here's this new product. Is this new product going to be used as a reactant? Let's see. Yes, it is. So this product is now used as a reactant. So I have another intermediate here. C6H6, CH2, CH3 plus another intermediate. So I have 2 intermediates off rip. Let me go ahead and underline those P. Okay. That's all I want to tell you about. Now let's go ahead and go further with the question. Which substance serves as a catalyst? So we've been talking about intermediates, and I want to get that out first, so it's easier for us to talk about catalysts. Now, catalysts are something else that's used in chemical reactions to what? Lower the activation energy so we can get from reactants to products faster, right? And so one cool thing about catalysts is that they're not used up in the reaction, but they are used to help lower that activation energy. So what we normally see with catalysts is they're usually going to be the first a reactant, okay? And then you'll see them reappear in usually the final product. Because again, they're not used up, right? And so for intermediates, just like we can cross them out because they're on the reacting the product side, catalysts, because they're a reactant initially, and then you'll see them in the final form, they also will be able to be canceled out. So I'm going to go through my new color and I'm going to look for things that are catalysts. So I have CH3, CH2, Br. It's starting at the first reaction and then AlBr3. We don't see any of them in our products here. That's fine. Let's go to the second reaction. We don't see them again. That's fine. The third reaction, our final reaction. Okay, I see AlBr4 minus. Oh, I see AlBr3. I see HBr. I see C6H5, CH2, CH3. But I don't see CH3, CH2, Br. So that automatically tells me AlBr3, because it's the first reactant and it's one of the final products, is a catalyst. So when they're asking me which one serves as the catalyst, I'm going to automatically choose AlBr3. We already know it's not this. That's an intermediate. We already know this one's an intermediate. We figured that out before. Okay? And so our catalyst will be AlBr3. It's the only one that's going to form as a first reactant and then finally reappear in the products, okay? And then AlBr4 minus is just a regular old reactant. So, we ain't got to worry about that. And that's how I actually approach question number 9. Now, remember, this says reactant, so let me go ahead and rewrite that. Yeah? Just so you know that when you're breaking these down, how to kind of start seeing what they are. All right, folks, that's number 9. Let's move on to number 10. All right, so number 10, it says the reaction 2A plus 2B is going to form C plus D proceeds by this mechanism. So they're giving us an overall reaction here, right? They're telling us a mechanism. We have something equilibrium, slow, and rapid. And it says the rate of the equation for this reaction is what? And so the first thing we want to do, similar to what we saw before, right? And what question number was that? That's going to be question number 5. We saw trying to give us a proposed mechanism and figure out the predict the rate law or the rate equation. They're calling it rate equation, same thing as rate law. That's what they want to do. So what we need to do is first, what? Identify the RDS step, the rate determining step. That's always going to be the slow one. So this is our rate determining step. That means anything after the rate determining step, we do not care about. Yep, I said it. We do not care about it. Okay? The rate determining step is going to determine the rate. So anything after that is not our problem. Anything before that, though, will matter. Why will it matter? Because this is the RDS is the second step. That means that, yes, we are going to have to get rid of some intermediates, just like we saw in number 5. So the first things first, let's go ahead and write our rates for everything that we see here. First, we have our stuff in equilibrium. That means our rate is equal to K forward, which is going to be A squared. And our rate is going to equal to K reversed, which is going to be A 2. All right? And that's simply all we have there. Now we got to go ahead and get our rate for our slow step. Okay? Which is going to be K2. You can call it K slow, whatever you like. It's going to be A2 and B. And then finally, I'm going to write their overall rate just so that we can identify our intermediates easier. And so our rate overall is equal to K. Then we have A squared, and then we have B squared. This isn't our true rate, right? We have to basically predict this mechanism, and that's all going to be based on that RDS step. Now, let's talk. We have A here, and we have B, but in our rate, we only have B and A2. So yes, this is our good old intermediate. And if we have an intermediate, what do we need to do? Get rid of it. Let's go ahead and try that. So the second step here is going to be setting our equilibrium rates equal to one another so that we can solve for the rate we're looking for, A2. Okay? So that means our K forward, A squared is equal to K reversed, A2. Divide by K reversed, divide by K reversed. So my A2 is equal to K forward, divided by K reversed, A squared. There we go. Now we're moving on. Now we're going to number 3, which is again, now we have our A value, our A squared value. We're going to substitute it into our slow rate. So our slow rate is equal to rate is equal to K2. Now we're going to substitute our A2 value. Now we have KF over KR, which is K forward and K reversed, A squared, B. There we go. Now what do? We got to simplify, folks. We're going to take this and combine it to 1K. And finally, we have our final answer. So let me go ahead and get this black. So we have our final answer. It's going to be rate is equal to K by itself, A squared, B. Now all I have to do is find this in my overall questions. Or sorry, answer choices. So this is A raised to the power of 2. That means anything that's not A raised to the power of 2, I'm getting rid of. So I'm going to get rid of A. Then we have B raised to the power of 1. This also has C and D involved, which are products, so we don't care about that. And this also has a product. So the only answer that would make sense would be D. Off rip, you could have got rid of B and C because they have products, which we don't use for our rates. Again, we care about initial amounts, which don't include products. And you also have situations where once you got down to letter A and D, then you can see that the only one of them have A squared. And so that's how you can get that answer too. All right, folks? So that is the conclusion of chapter 12. There's a lot to go off of, but it's all doable. You must practice, 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 use this to your advantage. We've been here for an hour, so let's just say it's probably going to take another hour just to do chapter 13. So even though I was talking all that stuff about it's going to be 2 hours long, not going to be 2 hours long, here we are, folks. I do apologize. Well, let's go ahead and get into chapter 13 and number 11. All right, folks, number 11. Remember, we got to change our brains because we're in chapter 13 territory now. And just to let you know, everything you learn in chapter 13 about rice tables, you're going to use for chapter 14, chapter 15, and some of chapter 16. Why? Because equilibrium does not stop here. Equilibrium can have to do with acid and bases. Equilibrium has to do with aqueous solutions that we're mixing together that have solids and liquids. So we have to start thinking of things in different ways. That means when you're starting to do your equilibrium questions from number 11 all the way to 20, make sure you're starting to orient your brain of how to approach it. So here it says, consider the following reaction, the following equilibrium concentrations, and equilibrium constant at a particular temperature. Determine the equilibrium concentration of SO3 gas. So there's multiple ways to do equilibrium problem. One way is you're probably just going to be given all the equilibrium amounts and you just have to solve for K. Or you're only given initial amount and you have to use a rice table to figure out equilibrium amounts so you can then solve for K, right? And a lot of times you are going to be given K, and there's going to be different ways that you can use K to help you make assumptions. Or of course, if you can't make assumptions, you have to use quadratic equation or the squares. Or if you have a lower number of reactants, for example, then you can get away with just solving for X with a small number of reactants and product too. For this question, since they already telling me they gave me equilibrium amount of a lot of stuff, they already gave me my Kc value, I don't need a rice table or anything. I just have to use my mass action expression from Kc to solve for whatever variable they want me to solve. So first I have my Kc value here, and what is it actually based on the chemical reaction? We're going to have SO3. That SO3 is going to be squared. It's going to be divided by SO2. That SO2 is going to be squared, and O2. Now, what do? We start plugging in what was given, folks. They gave us equilibrium amounts, not initial, literal equilibrium amounts. Well, there's no need for a rice table. We already have an equilibrium amount, right? So they gave us equilibrium amount of this. This is 0.0034 molar. They gave me equilibrium amount of this. This is 0.0018 molar. And they gave me the equilibrium constant. This is 1.7 times 10 to the 8th. Okay? All we have to do is plug things in. If I'm given this number, this variable, I can use it to solve for this variable, right, folks? And this is the only time I see people have issues is when they start doing excessive rice tables because they're not reading. If you're given equilibrium amounts, you do not need a rice table here. So make sure you are reading properly and taking your time so you can figure out exactly what you need and don't need. All you have to do now is manipulate variables. Another thing I noticed is that some students will be mixing up numbers here. So I'll see them map out everything properly. Everything looks great, pristine. But they accidentally put 0.0018 here and 0.0034 here. And so if that happens to you, you end up getting the wrong answer, of course, then you probably will end up with that 60% partial credit. So just keep that in mind. You want to make sure that you are taking your time with all these numbers. Now all we have to do is plug and chug and go ahead and solve. But before I do any plugging and chugging, I can actually map out using these variables here. So I can cross multiply my variables. I can say I have SO3 squared is equal to Kc times SO2 squared times O2. Then I can take the square root of both sides, okay? So that means my SO3 is going to equal to the square root of Kc, SO2 squared, and O2. And that's it. And I can use this to my advantage. Now, if you don't have to do this, you can go ahead and fill out all the numbers here, get the math, do whatever you like. I'm just showing you how it's coming together in my brain right now. All right, folks? So what do I like to do? I like to go ahead and get the numbers for every little part. Kc, we already know that. So that's going to be 1.7 e to the 8th. SO2 is 0.0034. So this is going to be 0.0034 squared. And so that's going to give me 1.156 e to the negative 5 molarity squared. And then this is just simply 0.0018 molar. All right. Now, when I multiply everything here, let's go ahead and talk. When I go ahead and I'm trying to get my SO3 concentration, I'll take the square root of all these numbers. So I have 1.7 e to the 8th I have 1.156 e to negative 5 molarity squared, and then I have 0.0018 molar. When I multiply these two, you see I'm going to get molarity cubed, okay? And so let's go ahead and get that. I'm going to write it down. SO3. Go ahead and get the number from inside. After I do all this math, I'm going to get 3.53736. Of course, it's molarity cubed, but once I take the square root of this number, that's going to get rid of 2 here, and I'll just have 1 molar left over, which makes sense because we're trying to get the molarity of this particular SO3 at equilibrium, right? So now all I have to do is take the square root of this. Okay. Once I take the square root of 3.53736, okay, I'm going to get 1.8807870069 molar. Again, we have to focus on significant figures, so let's go ahead and look at that. 2 here, 2 here, and 2 here. That means my SO3 concentration is going to be 2 significant figures as well. So I have to go ahead and round this one up to 1.9 molar. Boom. Just look for that on the answer choices. Letter A. And that's how I approach number 11. All right, folks. Some folks don't like mapping out variables. You don't have to. You can plug in all the numbers here and this cross multiply and then go further and do your square root later on. That's on you. I'm showing you my way of doing it. You don't have to do it this way. All right, folks. Let's move on to number 12. Okay. Equilibrium can be affected by many things. Temperature, right? Pressure, volume, concentration, etc., etc. So when we are considering the following reaction at equilibrium, which we have here, and it says, make sure that this is actually working, okay? It says, what effect will increasing the volume of the reaction mixture have on the system? As soon as they're telling you what effect will this have on the overall equilibrium system, we're thinking of good old Le Chatelier's principle, okay? Good old LP, Le Chatelier's principle, okay? And so what we have to do is start thinking of, if we have Le Chatelier's principle, the goal is if you have anything that's going to disturb the system, what's going to happen? The system is going to shift to the left or to the right to get back to equilibrium. That's it. And so the effect they're talking about here is going to be increasing the volume. Increasing the volume. The only way we relate volume is going to be through pressure. And why are we able to relate these? Good old 101, good old gas law, which is going to be Boyle's law. So P1V1 is equal to P2V2, okay? And so if I increase my pressure, I decrease my volume. And because of that, then I have the ability to say if I increase my volume here, then I effectively, therefore, am going to decrease my pressure. And that is where we're going to then start adding more details when it comes to Le Chatelier's. So volume, yes, we've increased it. You increase your volume and decrease your pressure based on the inverse relationship they had, okay? And so because of that, we got to make sure that we're utilizing our gas molecules now, since we're talking about pressure, in the right form. What does that mean for us? That means we have to focus on the number of gas molecules on either side to be able to figure out where the system is going to shift, left or right. So the first thing I do when I'm thinking of volume or pressure or any of those two, a lot of times they say increase or decrease in volume. They could just straight up say increase or decrease pressure as well. No matter what, that same Boyle's law relationship is going to exist. So what I do when it comes to volume and pressure is I first count the number of gas molecules on either side. You see this in gas state, gaseous state, gaseous state. You're only going to count the gaseous molecules. So I have 2 here and 3 here, 5 gas molecules here, okay? And then I have 2 here and 2 here, 4 gas molecules here. And understanding this is going to help you figure out where the shift is going to go. So if I increase volume and decrease pressure, then, let me make sure I write this here, decrease in pressure and increase in pressure. Just so we have everything separated. When I have a decrease in pressure, I'm going to have an increase in volume, just like we see in this scenario. And so the equilibrium or the system is going to go in the direction with more molecules. What type of molecules? More gas molecules. And of course, on the opposite, if I increase pressure and thus decrease volume, then it's going to go in the direction with less gas molecules. Okay? So we're dealing in a situation where we have a decrease in pressure, increase in volume. And so therefore, we're going to make sure we go from an area that is the least, and we're going to shift to an area that has the most. Okay? And so when we're thinking of our overall reaction, the most is going to be 5 gas molecules. So our answer, when they're telling us what effect will increase in the volume have, is going to say reaction shifts to the left. You also can say toward reactants. You can say whatever you like here. Some folks simply just put shifts left, and that's still correct. All right, folks? So that's how we'll basically approach this question. Let's move on to question number 13. Okay, question number 13 says the equilibrium constant is given for one of the reactions below. Determine the value of the missing equilibrium constant. Some folks might say, hold up, where is the overall reaction? Guess what? Excuse me. We don't always have to have an overall reaction when we want to couple equilibrium amounts, okay? So what does this mean? A lot of times we get our K values for one single reaction. But when you have a multi-step reaction, for example, or you're just coupling multiple reactions together, okay, the product of the equilibrium constants can be determined, right? The product of the equilibrium constant can be determined. So a lot of the times we have a K overall, and then we go through and we multiply our equilibrium constants, okay, K1 and K2, and that's what we're used to seeing. But you also have a situation that we see here, where again, we're just coupling two equilibrium equations together or reactions together, and we're given one Kc value, and we have to go ahead and figure out what the other unknown value is. And so what you first want to do is you want to go ahead and write the mass action expressions for both equations. So for example, for this first reaction here, and we'll call this one 2, number 1, we know that Kc is equal to 3.8 times 10 to the 4, right? And that also is going to equal to HBr squared divided by H2 and Br2. Okay, great. Now the second one, we don't know the Kc value. We do know the mass action expression is going to be H2 Br2, okay, divided by HBr2. Now, what we want to do is we want to use what we know and manipulate what we know to help us find what we don't know, right, folks? And so we have to say, what makes this K mass action expression different from this one? Where, as you can see, they're flipped. They're the reciprocal. And I'll tell you straight up, when I'm doing these questions, I just look at the equations. I never write the mass action. I'm like, okay, well, I see this is 2 here, this is here, so I obviously have to take and flip this one. And if I flip it, or I reverse the equation, then that means my Kc value is also going to be 1 over whatever that value is. So this is now going to be 1 over 3.8 times 10 to the 4th, right? That's the way I do it. If you're doing it this way, again, you're going to write all your math actions. You're going to see that all you need to do is flip this. This is over 1. So if I flip it, I have 1 over 3.8 times 10 to the 4th, which is equal to HBr squared divided by, oh, sorry, I'm doing the wrong one. Come on. Divided by H2, okay, Br2, and HBr squared. And so as you can see, now these mass action amounts are going to be similar or exact. And so if I want to find the Kc value, I just basically take 1 over 3.8 times 10 to the 4th, and I can actually get the value for this unknown, which is quite awesome when you start coupling things together. And just by taking the reciprocal or moving them around, it makes it easier for you, okay? So when I do 1 divided by 3.8 times 10 to the 4th, I get, and my significant figure should be 2 here, 2.6 times 10 to negative 5. That is the answer. Now this one's a little bit easier because all we have to do was basically flip this equation. But if you have to multiply, then you have to take your K value and you raise it to whatever you multiply by. Okay? If you have to divide, you're going to take your K value and you take it by 1 over whatever you divide it by. So let's say, for example, we multiply by 2. We multiply this entire thing by 2. We multiply by 2, we have to raise our K value to a power of 2. What if we had to multiply by 2 and flip it? that means we'll have 1 over our K value squared. You see what I'm saying? Now with division, if we have to divide by 2, it'll be 1 over 2 here. Or if you just take square root of K. If we have to divide by 3, it'll be 1 over 3. Divide by 18, it'll be 1 over 18. That's what we're talking about here. Okay, folks? And that's how I would approach number 13. And of course, extra little dilly-dallies if you have other types of questions. All right, folks, let's move to 14. Okay, number 14, it says, consider the following reaction. Xe, okay, plus 2F2 is going to be an equilibrium to form XeF4. All right, cool. A reaction mixture initially contains, there we go. When it comes to equilibrium problems, I've been talking about equilibrium. We've seen how to solve for K or maybe an equilibrium variable. Now we're talking about initial amount. When you're talking about initial amounts, you can use reaction tables or those Rice tables, or if people don't want to write the reaction again, we just simply call them ICE tables to help you understand how the initial amount and the change based on the reaction can get the equilibrium amounts, which therefore can get you your K equilibrium constant. Okay? Now again, we don't always have to talk about concentration. As you see here, a lot of atmospheres, which means we're talking about equilibrium pressure instead of equilibrium concentration. Okay, folks? When you're talking about equilibrium pressure, think partial pressures only. So here, they want us to find the Kp for this reaction. So we don't know the value of the Kp, but we can use our overall reaction to help us basically solve for the mass action expression. So it's still going to be products of reactants, but now because of partial pressure of Xe, F4, divided by the partial pressure of Xe, times the partial pressure of F2 squared. So we do get our mass action expression, and this is what they want us to solve for. Let's go ahead and do it. Now, it tells us that we have a reaction mixture that initially contains 2.24 atmospheres of Xe. So we got 2.24 of Xe, 4.27 of F2. All right, that's all they're telling us. And these are based on our initial amounts. So we can actually plug them into our equilibrium amounts here. We can set up a Rice table. I do like to be the one to rewrite my reaction, okay? But I kind of make it faster by not writing the states of matter. If it is liquid or solid, I just make sure I put a line through the whole thing so that I'm not confusing myself. We know when it comes to equilibrium, we're at standard temperature and pressure. We don't focus on solids and liquids at that point. Only going to be aqueous, gaseous, etc. Okay? So now, all we have to do is start filling our ICE table. I stands for initial. That's going to be any initial amount that's given. Okay, so for our atmospheres, it can be atmospheres, it can be bars, it can be millimeters of mercury, whatever units are given to you for that. For concentration, it's a little bit different though. We're talking about concentration, so we're talking about molarity. That means it should be moles per liter as your initial concentration. Okay, again, here we are dealing with pressure. So we have 2.24 atmospheres here, we have 4.27 atmospheres here. We know we have a zero product to start with. Now let's talk about the change. Really our goal is to figure out the amount of partial pressure over XeF4, right? And we were kind of completing this Rice table. We go through, we find our X value, and then we use the X value to help us figure out the rest of the actual amounts, right? But as you can see, the only way we'll be able to figure that out is if we can make an assumption with our K value. And we don't have a K value here. So if you don't have a K value, you've got to tell yourself, well, if I don't have a K value, or if I have a very large K value, or a very small K value, I know in some way you're dealing with quadratic equation in some shape or form, whether it's the squares, whether it's you have a small amount of reactants or products, or if you simply can just use what the equation is giving you to solve for Kp. When you're not given a Kp value, you also have to do whatever it takes to solve for that Kp value here. And so the change is going to be all about solving for whatever that change in X is going to be. So you're going to have minus 1. Okay, it's going to be related to the change in X. And again, the X is going to be the partial pressure of XeF4. Okay, and then you're also going to have minus 2X because we need 2 atoms or 2 moles or 2 molecules of this F2 in order to be able to get this product. Okay, and then we're just going to have plus X for the XeF4. Where am I getting these numbers? The coefficients that are in front of the compounds in the balanced chemical equation. Now for equilibrium, what do we have? We're going to have our 2.24 atmospheres minus X. We're going to have 4.27 atmospheres minus 2X, and then we're just going to have X here. What do we normally do? We finish the Rice table, right? We go forward further. We get our K value. We go ahead and figure out our X, and then we do everything that the question asks. But wait a minute, they give us something extra here. We're trying to look for our Kp value. We got to continue to read the question. If the equilibrium pressure of Xe is 0.34 atmosphere, so they're telling me an equilibrium amount of this. They're saying this is 0.34 atmosphere. They're giving me an amount for one of the variables. What's going to happen to our Rice table then? Well, I got to focus on Xe. They're telling me that my equilibrium, 2.24 atmospheres minus X, this entire thing is equal to 0.34 atmospheres. Okay? And so because that's 0.34 atmospheres, what can I do, folks? I can solve for X. I don't have to use quadratic equation. I don't have to do any extra math. I can solve for X straight up by using what's given in the question and the Rice table here. That's the reason why we don't have to end up using the quadratic equation. So sometimes, of course, you're looking at your K value, you're seeing you don't have one here, your mind is racing, you might start thinking, dang, I might have to use quadratic. But continue the question, continue with the ICE table, and then continue to read. I made my ICE table just based off this first sentence. And then when I continued to read, I found out that it already gave me one of my equilibrium values, which is my partial pressure of Xe here. So I can solve for X. How do I do that? Subtract by 2.4 atmospheres here. Subtract by 2.24 atmospheres. So minus X is going to equal to minus 1.9. So X is equal to 1.9 atmospheres. That is powerful. Now what can I do with it? I can take my 1.9 atmospheres and use it to X to fill out the rest of my overall Rice table. And if I'm filling out my Rice table and I'm telling you X, what am I doing? I'm giving you my equilibrium amounts. So I can take this 4.27 atmospheres minus 2 times 1.9 atmospheres, okay? And that's going to be 4.27, okay, minus 3.8, and that's going to give you 0.47 atmospheres. So now I got my partial pressure of F2, booyah. And now for Xe(F4), that's easy. It's just 1.9 atmospheres. That's it. So now that I have all my equilibrium amounts for every single species, all I have to do is plug in the values to solve for Kp, excuse me. So I have Kp, my partial pressure of Xe(F4), 1.9 atmospheres. Partial pressure of Xe, no, it's not 1.9, because I did have a lot of students who just say, oh, well, it's automatically 1.9. No. They gave you that number. This is 0.34 atmospheres. They already gave you that number, okay? And then finally, we have our 0.47 atmospheres. And that's going to be squared. Now, again, why is this 0.34 and not 1.9? Again, you had to use the fact that you got an equilibrium value to solve for X. In order to get Xe, it's 2.24 minus X. So if I took 2.24 minus my 1.9, that's how I'll get my 0.34 here, folks, okay? So make sure you are keeping that in mind. That's how everything connects. So now let's go ahead and do the math. Again, we do have this one that's going to be squared, so I'm going to just do this one separately. 0.2209, and this is now going to be atmosphere squared. But of course, because of the constant, equilibrium constant pressure, we do not care about units here. So let's go ahead and do the math here. I'm going to write my answer up here. I'll do 0.2209 times 0.34. Keep that in my calculator. 1.9 divided by my answer is equal to, how many significant figures should we have? We have 2, 3, and 3. So our answer should be 2. I'll get 25. That's the letter A. All right, folks, let's go to number 15. Okay, number 15. Now, as you can see, we are with equilibrium, chapter 13 again, right? So let's make sure that we're keeping that in mind. And it says, consider the following reaction. So we have this reaction here. A reaction mixture initially contains. I'm telling you, it's so much easier when they just tell you initial, because that automatically thinks Rice table. Literally, the I stands for initial. So it just makes it easier for you to think of Rice table. If they don't give you that, you do have to make sure that you're pulling out information from the question. So we're going to do the best we can with this. Okay, reaction mixture initially contains 2.8 molar of H2O, 2.6 molar S2O. Okay, we have this and we have this. Determine the equilibrium concentration of H2S. They only want the equilibrium concentration of this. If Kc for the reaction at this temperature is 1.3 times 10 to the negative 6. So we're now going to get an ICE table, but this time they give us a equilibrium constant value. So they told us Kc is equal to 1.3 times 10 to the negative 6. And we know this is going to equal to H2S squared divided by H2O squared times SO2 squared. And why do I know that? Because I have everything and I'm missing a freaking product. This is O2 cubed, apologies. Why do I know all this? Because all my states of matter are gases. So there are no solids that I don't have to add into my overall mass action expression. Okay? Now, what else do they give me? They don't give me any equilibrium amounts, folks. This time is not like the previous. They don't give no equilibrium amounts. So I have to go straight up Rice table. And because I have to go straight up Rice table, I have to be able to ask and make different assumptions. And so let me set up my Rice table first. Go ahead and do that. And then we'll talk about assumptions after. We have 2H2O plus 2SO2, equilibrium 2H2S plus 3O2. Now we already have the initial amounts for this. This is 2.8 molar. This is 2.6 molar. The change is going to be minus 2x here, minus 2x, plus 2x, plus 3x. Okay? Now here, we're going to have 2.8 molar minus 2x, 2.6 molar minus 2x. Here we just have simply 2x. Here we have 3x. So we have our perfect Rice table. Now the question becomes, oh man, do I have to do quadratic equation? Yes or no? It all going to depend on that K value. Okay? This is a little trick I use. I use 10 to the 3 and I use 10 to the negative 3. If your number is 10 to the 3, okay, you're using quadratic equation or the squares or something, meaning you can't use an assumption. So if it's straight up 10 to the 3, no assumption. If it's straight up 10 to the negative 3, usually you can't use an assumption there. But if your K value is 10 to the 4th, so anything higher than 3, and so sometimes I just say 10 to the 3 plus, okay? Yeah. 10 to the 3 plus, or 10 to the negative 3 plus, meaning you can have like say 10 to the 4th, or you can have 10 to the negative 4th. Then for these, you can assume. Because the number is smaller and large enough where you can make that assumption. Okay? But again, if you don't have that, you can't make that assumption. So for us, our K value, looking here, is 1.3 times 10 to the negative 6. That negative 6 is larger than 3, okay? And so this is a smaller number. That means I can make an assumption. An assumption for what? It means anything that is going to be my initial amount. Usually we make an assumption, we have an initial amount, subtracting by the amount that's reacting, it's going to give you your equilibrium amount, right? What if the amount that's reacting is negligible? So if that amount doesn't matter, then your initial is going to equal your equilibrium amount. And guess what? That's what we can make that assumption. If our K value is small enough, like we see here, then again, it's going to be negligible. And so because of that, our initial amount is going to equal our equilibrium amount. So we can just get rid of our minus 2x here. Even if this was plus 2x, we can get rid of that as well. Either way it goes, we're getting rid of it. Okay? Why is this going to be important? When we're trying to solve for something, then you want to make it easier for yourself. If I can use an assumption, I'm going to use my assumption and move forward. Let's go ahead and get the work in now. They want us to figure out the equilibrium concentration of H2S. We already know what the equilibrium amount of H2S is. It's going to be 2x. So now our goal is to solve for x. Let's go ahead and do that. So again, I'm going to have my Kc value here. We know this is 1.3 e to the negative 6, and I'm going to plug in everything that I see here into my mass action equation. So H2S is going to be 2x squared, 3x cubed, divided by 2.8 molar, this is squared, divided by 2.6 molar, and this is squared. So 1.3 e to the negative 6 is going to equal, you got to make sure you're doing the math here. So let me just talk. So first things first, this squared is going to go here and here. So I'm going to have 4x squared times, this cubed is going to go here and here, 27x cubed. Okay? This 2.8 here is going to be 7.84 molar squared. This is going to be 2.6 squared, which is 6.76 molarity squared. Okay? Now we know the goal is to get down to a unit of molarity because they're asking us for an equilibrium concentration. Now let's go ahead and continue on. Continue on over here. So we're going to have my 1.3 e to the negative 6. Now I have to make sure I'm doing this properly. So 4 times 27, that's going to be 108. When you're multiplying x squared and you're multiplying x cubed, you have to add them together. So 3 plus 2 is going to be x to the fifth. Divide that by 7.84 times 6.76. That is going to be 52.9984 molarity. Okay? This is also going to be molarity to the fifth here. So this is going to be 52.9984 molarity to the fourth. So as you can see, we get rid of this one. We're only left with molarity, which is our needed. Once we get down to this, then we're home free kind of, right? We just got to cross and multiply here. And so we cross and multiply, we're going to end up getting 108 x to the 5 is equal to 6.889792 e to the negative 5. Right? Now we're going to divide by 108 here, divide by 108. And now we're left with x to the fifth is equal to, let's go ahead and do this division. I get 6.379437 e to the negative 7 molarity. Go ahead and get a different color here. All right, now we've gone down to here. What do we have to do to isolate x? We have to take the fifth root. So normally if we have x to the third, we are going to take the fifth root or the third root of each side, right? So this time we're just going to take the fifth root, and that means in your calculator you have to press the number 5. Then you're going to hit second, okay? And you have to use the square root that looks like this with the little x. So when you hit 5, that's going to actually substitute the x. You hit second, you hit this value, which for me on my calculator is right where the little hat symbol is, okay? So I'm going to hit 5, second, hat symbol, and then I'm going to enter 6.379437037 times 10 to the negative 7. You know I'm hitting it up in parentheses here. And then I press enter, and that gives me my number, okay? Let me go ahead and erase all this so we can go ahead and get our number. Now for this on the exam, if you still have issues with your calculator, you need to speak up. That's something I'm willing to help with because that's a nightmare, okay? That's a complete nightmare, so please speak up for that. Once I take the fifth root of this number, I get x is equal to 5.76708, okay? 6576 times 10 to the negative 2, and this is molarity. Now that's not the end of it because we need to go ahead and figure out the equilibrium concentration of H2S like this question asks, right? So if I already got my x value, I just have to look at what my equilibrium amount for H2S is, and that is equal to 2x. So I'm going to take 2 times the 5.76 times 10 to the negative 2. And so my concentration of H2S is equal to, and how many significant figures? Let's see. 2, 2, 2. So we have 2 significant figures. It means when I do all the math, I'm going to get 0.12 molar. That is my answer, folks. And what am I doing? I'm blocking it around. I'm circling it. Whatever way you can see. I do want to talk about something else as well here, though, because there is another little way to make an assumption outside of like the 10 to the negative 3s and stuff like that. Just erase this here. You can look at the initial amounts and relate them to the K value. So for example, if I take my initial divided by my K value that's given, and that's greater than 400, I can make an assumption. And it's really for any of them. So I'm like, okay, I can take 2.8 because they gave me 2.8 molar H2O, right? So if I take 2.8 divided by my 1.3 times 10 to the negative 6, I get like a really ginormous number, which is way bigger than 400, which is another way I can say I can make an assumption. So obviously if you get less than 400, then you can't make the assumption, right? So that's another little way you can do that there. Let's move on to number 16. All right, folks, let's get into number 16. It says, in which reaction, so I just want to know which specific reaction of the ones listed, will an increase in total pressure, hold up, they're saying an increase in pressure at a constant temperature favor formation of the product. We're taking the Chalet's principle and going a little bit further here now, right? Off rip, let's go ahead and talk about increase in total pressure, everything we know about it. We've seen this question similarly to number, I forgot which one it was. Let me go ahead and look back, number 12. So we've seen kind of an idea with the pressure and volume and things like that. So we know when you increase pressure, you decrease the volume. And we know that when you have an increase in pressure, you're going to go in the direction with less gas molecules. Now, this is interesting because they want you to automatically favor the formation of the product. They told us that specifically. So what we're looking for here is we're looking for something with a larger number of gas molecules and the reactants so it can move to our product. That's really what this question is at. So we're looking for a higher number of gas molecules in the reactants so that we know, because we're increasing the pressure, that automatically it's going to go to the area with lower gas molecules, which would automatically be the products. So if I'm trying to favor the formation of products, I'm going to favor whatever one of these actual equations here are going to have a large number of gas molecules in the reactant so that when I increase total pressure, it will move into the direction with the least amount of gas molecules. That's what they're doing. So now all we got to do is go through A, B, and C and just straight up count up the number of gas molecules. So for letter A, this is 0 gas molecules here because we have a solid, and this is 2 gas molecules. So if I increase the pressure, it's going to go into the direction of the reactant. So since it's going towards reactants and not products, I don't want that. Let's move on. H2 and Cl2. So we have 2 gas molecules, and then we only have 2 gas molecules. So since they're 2 and 2, they're going to be in equilibrium. We can't worry about that. Let's do the third one. We have 3 gas molecules in equilibrium with 2 gas molecules. So if I increase the total pressure, then guess what? This will go to the products. And so that one works. Now let's go to letter D. We have 1 gas molecule and 2 gas molecules. So if I increase the pressure, I'm going towards reactants. And so the only one that's going to go towards products when we increase the pressure will be letter C. And that's how I approach number 16. Okay, number 17. The equilibrium constant for the gaseous reaction, C plus D, in equilibrium to form E plus 2F, is 3.0 at 50 degrees Celsius. So they're already telling us what the equilibrium constant is. So I know my equilibrium constant is equal to 3.0, okay, at 50 degrees Celsius. I actually can write my equilibrium mass action here. E is going to be F squared divided by C and D. There we go. All right, so just from the first sentence, that's what I had. Then it tells me in a 2-liter flask at 50 degrees, so we know our volume is 2.0 liters. All right, you have 1 mole of C, 1 mole of D, 1 mole of E, and 3 moles of F are placed. Okay, so they gave me my equilibrium amount, but now they're giving me moles of these different species as well. That's it. So they gave me all the moles for that. Let's go ahead and read it and continue. Then it says initially the reaction will. If they give me equilibrium, they give me number of moles and volume, I can find my initial concentration. And if I have initial concentrations and not equilibrium concentration, then guess what? I'm no longer talking about K. I'm now talking about Q. So if they're focused on what the initial reaction would be, then I would have to get my E value concentration, my F concentration squared, my C value concentration, and my D value. And because these are all considered initial amounts, I'm going to take my 1.0 moles here divided by 2.0 liters. I'm going to take my 1.0 mole here and divided by 2.0 liters. I'm going to take my 3.0 moles here and divided by 2.0 liters. And I'm going to take my 1.0 mole here and divided by 2.0 liters. That way, I can figure out the concentrations of each of these species initially, because that's what they gave me, right? And because I'm talking about initial amounts, something outside of equilibrium, I'm talking about Q. And anytime a question has you talking about Q and K, they're going to want you to compare them, folks. So what happens when Q is equal to K? What happens when Q is greater than K? And what happens when Q is less than K? This is the information they want you to pull out. And so you would have to understand that, oh, they gave me an equilibrium amount, it got us here, but because they want us to figure out the initial amount, we have to think about Q. All right, so we know this is going to be at equilibrium here. That's easy. That means the products and reactants are going to be similar here, okay? And so that means we got to focus on when we have Q being greater than K or Q being less than K. When Q is greater than K, the reaction is going to proceed to the left. When Q is, of course, less than K, the reaction is going to proceed to the right, okay? Why does this matter? Well, we also are thinking about product and reactant concentrations. So let's say Q is equal to product concentration divided by reactant. So when Q is way larger than K, okay, you have an increase in the product here. You can see if I have a large number here and a small number here, my overall value is going to be greater. So that means you have a lot of products. What do you need to do? You need to get rid of that product. We're talking about equilibrium. So I need to decrease my products in order to get back to equilibrium. So if I decrease my products, I'm going to effectively increase my reactants, right? Now let's look if our Q is less than K. If our Q is less than K, that means we probably have 1 over, say, 10 or 100. And it gives us a small number here, meaning our reactants are increased. We have a lot of reactants. So in order to get back to equilibrium, we want to then decrease our reactants. So if we're decreasing our reactants, that's going to allow our products to get back to the value they need to be at for equilibrium, okay? And so the reaction is going to proceed to the right. So what we need to do is, if we already have our K value, we just got to use our calculations to find our Q value. And then we compare. Number one, let's go ahead and get our Q value. Now, 1 divided by our 2.0 is going to give us 0.5 molar. Of course, I'm doing the math here so I can get all of my concentration amounts. And then 3 divided by 2 is going to be the 1.5 molar. This is squared because that was F. And then for C, we're going to have 0.5 molar. And then for D, we're also going to have 0.5 molar. So my Q value, let me go ahead and do this as well. This here, once I square it, is going to be 2.25 molarity squared. Again, the units are not going to matter because we're talking about Q and K, so you don't really have to focus on those too much. You can also just get rid of 0.5 here and just divide these two. That might make it easier for you as well, okay? I'm just, again, showing you what I did. So I'll get rid of those, and I have 1.5 squared. I'll have 2.25 divided by 0.5, and that's going to be 4.5. So now that we know our Q amount, now we're going to say, okay, our Q is equal to 4.5. Our K is equal to 3.0. That was given. That means our Q is greater than K. When our Q is greater than K, we're going to have more products. And so that needs to decrease. And so we're going to shift to the left. And what does that also mean? That means that we're going to have an increase in reactants as well. So we can't add just little bits of more information. Now let's go ahead and read our answer choices. That's all it's about now. Letter A. Initially, the reaction proceed at equal rates in both directions. No, it hasn't even got to equilibrium yet. It's initial, right? And then letter B, proceed more rapidly to form E and F. E and F are both products. So because we know Q is greater than K, we already have a lot of product. So we don't need to form any more. So this definitely would not be correct. It would be correct if Q was less than K though, right? But it's not less than K. Finally, we have letter C, proceed more rapidly to form C and D. We know this is true because it needs to proceed more rapidly to form reactants, and that's the only way we're going to get rid of products so we can go back towards equilibrium. This Q value is way too big, so we're going to decrease our products so we can go back to equilibrium by shifting to the left and therefore start producing our reactants more. And so letter C definitely works, right? Let's look at letter D. Do not occur in either direction. That doesn't make sense. We're talking about equilibrium, and equilibrium means that you're going to go in a forward direction and a reverse direction. So don't get caught up with this kind of terminology. It says do not occur in either direction. No, it's going to occur in some direction because otherwise we wouldn't be studying equilibrium, right? So I can get rid of that one here, and that means my answer choice would be letter C. All right, folks, let's move on to number 18. Okay, so this question says, consider the reversible system at equilibrium. Boom. Well, well, well. We have a new little sneaky little treat for us here, and that is going to be heat. Now we have heat as a product, so automatically I'm thinking this is exothermic, okay? So just by looking at this, I'm already having in my brain some stuff. So I'm like, okay, we have heat. Heat is a product, so we're probably looking at something that's going to be exothermic. They didn't specify that though, all right? So we're just looking at it as heat. Then it tells us when the temperature is increased at a constant pressure, here are the answer choices of what potentially can happen, and figure that part out. So first, if I'm dealing with heat, I know that heat is a product. I'm probably dealing with something that's exothermic. So likes to release heat, okay? If heat is going to be a reactant, I'm usually dealing with something that's endothermic. It needs to absorb heat. Okay? Okay, since we're talking about something that is going to be endothermic, then let's just focus, or exothermic, let's focus on that. So exothermic, and I'll write endothermic on this side just because why not? Because there's a lot of little details that you learn, and this is going to be something that's going to help you map things out. So when you have something that's exothermic, that means that we usually are going, when you have an increase or you're going to add temperature, let me just say that. So say I'm going to add temperature here, or I'm going to remove temperature. Now, of course, for our question, they're adding temperature, so we'll be able to answer that in our answer choices after we get our notes down. So if I'm going to add temperature, everything is all about Q and, of course, K. So we need to make sure we keep in consideration our product and our reactant concentration. Same thing here. If I add or remove, it doesn't matter. I'm still thinking about Q, which is my product concentration over my reactant concentration for everything. That helps us basically get these answers down. Now let's go ahead and fill out some information. So when I add temperature, that means I'm going to be increasing my heat. And so a lot of times you're going to see our Q values. Our Q value is going to be less than our K value when you start adding temperature for an exothermic reaction. Okay? Our Q value is going to be less than our K value. Why would that happen? Well, if I'm going to be adding temperature to something that's exothermic, then that's going to end up causing an increase in the overall amount of reactants. Why? Because it's basically like I'm adding heat to the product side. So if I'm adding things here, everything here has to decrease, and the reaction is going to end up shifting to the left. And so because it's shifting to the left, I'm going to end up having an increase in reactants and a decrease in whatever products I have. And this is just simply by using heat as a potential product. Remember that heat's going to affect everything. When I remove temperature from something that's exothermic, my Q value is going to be greater than K. And so because here, when it's going to be greater than K, I'm going to shift to the right, okay? And so because I'm shifting to the right, what's going to end up happening? I'm shifting to the right, I'm going to have an increase in products and a decrease in reactants. So I have a decrease in reactants here and an increase in products. Now we can stop here and just answer the question based on exothermic. And of course, why not just keep going forward and talking about endothermic? Okay, same thing here. With endothermic, it's opposite. So when you add heat to something that's going to be on the reactant side, guess what? Your Q value is actually going to end up being larger. And so what's going to happen is you're going to decrease your reactants and you're going to increase your products so that your reaction is going to shift to the right. That makes sense. You're adding heat to the reactant side. It's almost like adding a reactant. And so you have to shift to the right to get back to equilibrium. So if I'm going to remove heat, then that means my Q is going to be less than K. Now, when my Q is less than K, what is going to happen? We already saw it. We know it's going to shift to the left when my Q is going to be less than K. So when that happens, I'm going to have my increase in reactants and a decrease in products. What that means is I'm decreasing my product amount so that I can have an increase in reactants. And so I'm going to shift to the left here. So again, I use my Q and K, just like we had before, to help us understand how to figure out which way our overall amounts are going to shift. And it really does depend on if it's exothermic or endothermic. We can't just go over basic, because in the previous questions, like question number 17, we got you to say, okay, Q versus K. Q is greater than K, so it's going to proceed to the left. That's when we didn't have heat involved. With heat involved, these are going to change, as we see here, right? So you have to have a little bit of detail about that. Some folks should simply just remember, hey, heat is a product, it's going to increase, so I have to shift to the left no matter what. And some people are just going to remember it that way. And now that we have our details, let's add more to it. So when the temperatures increase at a constant pressure, what's going to happen? We have heat as a product, so we're going to be talking about here. If we're going to increase or add temperature to something that's exothermic, we should be shifting to the left. We have a decrease in products and an increase in reactants. Okay, so letter A, the CO2 concentration will be increased. True or false? This is CO2. Would this concentration be increased? And this is a product. No. Product concentration will be decreased if we're going to add temperature to an exothermic reaction. Why? Well, because if we're adding an increase in the product, we need to decrease our product amount to get the correct number of reactants in order for it to shift to the left. Okay, so we are actually effectively shifting to the left here. Part B, or letter B, the CO2 concentration will be decreased. That's true. We know our products are going to decrease. The amount of each substance will be unchanged. That's untrue because that will be at equilibrium, and we're not. We're saying that we're going to have an increase, which will affect Le Chatelier's principle. The only time that you won't have an effect on Le Chatelier's principle is if you use something like a catalyst. So if we had a catalyst here, then letter C would be our answer because nothing will change. The catalyst does not change anything in the reaction, right? But we don't have a catalyst. We're talking about heat, and we're talking about an increase in heat. Letter D, the amount of each substance will be increased. Well, if the amount of each substance is increased overall, then that means heat doesn't really have an effect on the products or reactant side. It means if I add heat, it's just going to increase everything overall, and everything is increased, and that doesn't really help us with equilibrium. So that one's definitely out. And then the results cannot be predicted from the information given. The reason why this one is wrong is because we already have a correct answer for B. So the question becomes, can I verify that B is correct? We go back to our information and say, well, the only way it's going to happen is if I increase the heat, I have to decrease my products. So yes, I can verify that B is correct. And that is my correct answer, folks. That's why I get through number 18. All about coming out with some notes from yourself. But again, if you have that chef's kiss and you know, hey, if I increase in a product, I'm going to shift to the left. Have that information can allow you to get to B as well. Okay. So it really just depends on what you like to do. Okay. So for number 19, we're back to what we had before. We have a certain temperature at equilibrium constant for the reaction, at a certain temperature, the equilibrium constant for the reaction 2HI is an equilibrium to form H2 and I2 is 0.49. So just off of that, we can go ahead and get our K value, we can get our mass action, and we can go forward. Okay, so I'm going to go ahead and write my K value. I'm like, okay, my K looks like we're talking about equilibrium amounts, so it's Kc values and this is concentration is equal to 0.49. We know this is equal to H2, I2 concentration divided by HI squared. So that's what we know from the first sentence. And it says, calculate the number of moles of hydrogen produced. So they want us to know the number of moles of hydrogen produced or formed, okay? When 1 mole of HI is placed in a 1 liter vessel at this temperature. So they said, hey, I want to know what's the moles of this H2 equilibrium value if I have the initial amount of this value. So if you're given an initial amount, what does that mean? You have to use a Rice table. Okay? And so how do I know it's initial? It's because they told me that 1 mole is placed in a 1 liter vessel. And so because they're placing it, that's like they're starting this whole thing off, right? And so that's how I kind of keep it in my head. Oh, we're talking about Rice tables again. Anytime we're thinking of initial, you're starting off, you don't know equilibrium amounts, you have to do a Rice table to get those equilibrium amounts. So then you can then figure out whichever they're trying to ask you to figure out. Okay. So my Rice table, I have my 2HI. I'm going to break down to H2 and I2. Now, what else can we get from this? Guess what, folks? We also can make an assumption. So we saw from our K value from number 15 that we can start making assumptions. Here's our K value here. Our K value is 0.49. Automatically, I'm telling you, we're in quadratic equation land. No, you cannot make, with a K value like this, no, you cannot make an assumption. So you either have multiple choices. Now, you have to think about this. If I told you you're not going to have quadratic equation on the exam, and you run into a situation like this, do not use a quadratic equation because you already know I'm not going to give you that. So what else can you use outside of quadratic equation? Okay, the squares. When you have a perfect square, you can solve for the x value that way. Or if you have a small number of reactants and products, you also can just easily solve for x that way. So for us here, we know we're not going to use quadratic, so we're either going to have an easy way to solve for x, or we're going to use the squared. Okay. And so that's what you want to make sure that you're reminding yourself of, because if not, some folks automatically see this, they automatically go to quadratic, and you're doing extra work for yourself. All right, next, let's talk about initial. So we got the initial amount of HI, but they only gave us 1 mole of HI, and they gave us 1 liter. So to find the concentration, we're going to take mole divided by liter, and that is going to be 1 divided by 1 mole divided by 1 liter. That's equal to 1 molar. So this is simply going to be 1 molar. This is 0, and this is 0. We're just filling out our Rice table now, folks. This is going to be minus 2x. This is going to be plus x and plus x based on the stoichiometry of the balance equation. Next, we're going to go ahead and fill out everything. We have 1 molar minus 2x, and then we have x here and x here. Now again, what's the issue here? We cannot get rid of this minus 2x. We cannot make an assumption. We have to keep everything the way it is. So let's go ahead and get our Kc value, which we know is 0.49. This whole thing is going to equal to x times x, which is going to be x squared, divided by 1 molar minus 2x. And this whole thing is squared as well. Well. Remember I told you either you're going to have an easy way to find the x or you're going to use the squares. Guess what? We're using squares. So again, you're never going to use quadratic on a real exam. So make sure you're thinking of squares value at this point. That means I can take the square of either side. And so the square root of 0.49 is going to be 0.7. This is going to equal to x over 1 molar minus 2x. Now I can use this to solve for x. So what do? I'm going to cross multiply here. So x is going to equal to 0.7 times 1 molar minus 2x. I'm going to take my 0.7 and factor it here. So my x is now going to equal to 0.7 molar minus 1.4x. So I'm going to add 1.4 to either side. Of course, there's a 1 in front of this. So I'm going to have 2.4x. There's a 1 here, so I add those together. 1 plus 1.4 is 2.4x is going to equal to 0.7 molar. Divide by 2.4 here, divide by 2.4 here. Therefore, my x is equal to 0.29 molar. So automatically, folks are like, okay, we got it. Let's go ahead and get our answer. But they want us to figure out the number of moles of hydrogen. So I have to look at my hydrogen here. My hydrogen equilibrium is going to be H2 is equal to X, which we know is 0.29 molar. But wait, they want number of moles. They don't want molarity. So what do I need to do with my answer here? And I'm erasing it because it's the same situation. What I have to do with my answer here is I have to make sure I'm going from molarity to moles. So molarity is equal to mole over liter, so I can cross multiply to get my molarity. If I take molarity and multiply by my volume in liters, I can get my moles. So I'm taking my molarity of H2 multiplied by my volume that's given, 1 liter, and that is going to be 0.29 moles here. And so the answer is C. Now this one was easier. A lot of times people say, well, it's obviously X. No, this is molarity, this is moles. In this type of question, when you got 0.29 for your X, you could have easily got the right answer, right? Correct. But what if it wasn't a 1 liter vessel? If it wasn't a 1 liter vessel and say a 2 liter or 3 liter vessel, then you're going to have a different number for your H2 value. And so if you have a different number when you're converting from molarity to moles, that's where you want to make sure you are just consolidating every single step that you're doing here. Otherwise, it can be very easy to get mixed up. Okay? And just to let you know, all the questions that you're seeing throughout are going to be ACS exam type questions. So that's the reason why I've increased the number of questions here. We have 20 for the exam, and there are just a myriad of questions, all different flavors of questions you can see on that type of exam. So just keep that in mind as well. Okay, folks, let's move on to our final question. We have made it to the end. Yay. And our final question says, consider the following reaction. So we're dealing with equilibrium again, right? And so just remember, when you're dealing with equilibrium, you have to be able to know how to do this work. If you don't, then the issue is going to become that when you get to 14, 15, 16, etc., you're not going to be able to understand anything. Because a lot of it is the foundation is being able to recognize, pull out, manipulate variables for these equilibrium ice tables, and then be able to use that information to apply it to acid-base equilibria, aqueous equilibrium, everything. So you got to make sure you have a good foundation here. Chapter number 20, not chapter. Number 20 is consider the following reaction. You have everything as gaseous is here. Now, the only time that things can change is if you don't get gaseous. So I want to speak on that really quick, just in case. So say this is a solid. When I write my K values for this, because everything's in molarity, if this was a solid, then I have my products, CS2, my reactants, H2 raised to the power 4, and then I will not write CH4. I'll just write H2S squared if I had this as a solid. Okay, and that's if the reactant was solid. What if one of my products were then solid? So say this one was a solid. That means my K value would be CS2, so I would not include H2, and then CH4 H2S squared. Okay, what if both of these were solids? That means I would just have 1 over whatever that is. All right, what if both of these were solids? You can just always keep that in mind. If both of those are solids, then my Kc value is simply going to be CS2, H2 raised to the power 4. Okay, because it'll be over 1, so there's nothing legal right there. So you have to make sure that, yes, in these practice exams, homework and stuff, you're given that, but sometimes, in a real exam, I might just throw you out a solid. And so you just want to make sure that you understand how to read and do all these different reactions, okay? Erase that before we get started. All right, it says the reaction mixture initially contains 0.5 molar CH4, okay, that's one reactant, 0.7 molar H2S, that's another reactant. If the equilibrium concentration of H2S is 0.44, find the equilibrium constant Kc. Well. Now, this is pretty much similar to number 14, but instead of using equilibrium pressure, we're using equilibrium concentration. Okay? So we need to figure out the Kc value. I'm going to write the mass action expression. Again, we're going to have CS2, we're going to have H2 raised to the power 4 divided by CH4, and then we're going to have H2S raised to a power of 2. Now they're already telling me my equilibrium amount of H2, I can put in here, is going to be 0.44 molar. So they already told me that. I can use that to my advantage when I create my Rice table. So again, when they don't give me a Kc value, I can't make any assumption. I automatically should be thinking of quadratic equation. But you know you're not going to be using a quadratic equation on this exam. So again, what you need to do is, if they give you an initial amount, write out your Rice table, just like we did in number 14, and use your Rice table to solve for the equilibrium amounts here. Okay? And the reason why we can do that is because they already gave us an equilibrium number. They already gave us a concentration of H2 at equilibrium. We can use that to solve for X just by using the Rice table and then just plug and chug, just like number 14. Let's go ahead and write our overall reaction. Let's go ahead and write our initial amounts, which they gave us here, 0.50 molar, 0.75 molar, 0, and 0. The change here is minus X. This is minus 2X. This is plus X. This is plus 4X. All right. Now we have to write our equilibrium amounts. So we know that this is 4X, and this entire thing is equal to 0.44 molar. We also know that this is 0.50 molar minus X. This is 0.75 molar minus 2X, and this is simply X. So if we already know that this 4s is equal to 0.44, we divide by 4 here, and we get our X is equal to 0.11 molar. So our X now we're going to plug into all of our equilibrium amounts so that we can solve for Kc. So this is going to be 0.11 molar, okay? This is going to be 0.75 molar minus 2 times 0.11 molar. And so that's going to equal, double check I have everything, 0.53 molar. And then I have over here 0.50 molar minus 0.11 molar. And that is going to give me 0.39 molar. So I have all my equilibrium amounts. Now I'm just going to find my Kc value. So first, I'm going to put my CS2 concentration amount, which we found at 0.11 molar. Then I'm going to find the amount that was given for H2. It already gave me that amount, 0.44 molar raised to the power 4, divided by my CH4. My CH4 amount is 0.39 molar, and my H2S amount is 0.53 molar, and this is going to be squared. You know what I do? I like to go through and get all my little numbers here. So 0.44 raised to the power of 4 is going to be 3.748096 e to the negative 2, or times 10 to the negative 2, molarity raised to the power of 4. 0.53 squared is simply going to be 0.2809, and that's going to be molarity squared. Again, units don't matter because we're talking about our constant value. So if I take my 3.74 times 10 to the negative 2 and multiply by 0.11, I get 4.122905.6, okay, times e to the negative 3. This is going to be molarity. Okay, still going to be molarity as my units, but again, they will cancel. And this is going to be divided by 0.2809 times 0.39, okay? And I get 0.109551 here, okay? So when I do my math, what is my answer? And again, how many significant figures should I have? So I should have, I got 2 here, 2 here, so I should have, and 2 here. So I should have 2 significant figures all together. I get 0.038 as my final answer, and that is letter B. So again, by my final answer, I start thinking about significant figures, and that is practice exam number 2, knowledge. And my guidance is going to be less than exam number 1. And my guidance will continue to decrease until you don't get any more guidance at all as the exams continue in the semester. Again, this means I will not give you the strategy to get through, but you must have some type of information on the page. If you don't know anything or don't have any background, you will have to take the points that you are going to get for that particular question. Again, study, create strategies to approach questions, and use the formula sheet. The focus is going to be practice, 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 especially, because we have so much math involved in chapter 12 and 13. You must put in the time it takes to learn effectively. And that means including that strategy and approach. Sometimes I see folks have done the homework, they practiced and they reviewed, but they really don't know how to approach this question if it was given in different ways. Of course, it's easy if the practice exam and the real exam are similar, but if you're given a question that's different but with the same information, are you still able to answer that or find a way to approach it? That's how you know you've done some more of level of the work and tried to put in some kind of approach or understanding. And of course, you do not need to cheat for this exam. Number 1, for chapter 12 specifically, you're given basically every single equation necessary for 0, first, and second order. You will also be given the same exact chart for the final exam as well, unless something changes. Okay, folks? So you want to make sure that you understand how to utilize every single equation that is going to be given to you and use it effectively to help you throughout. All right, let's get started.